between degenerate and non-degenerate fields. So for certain values of the dimension, delta RS, which are of this type here with integral RS, the primary field delta when it has a descendant which is itself primary. So that's called the null vector. And then you decide if you want to set this null vector to 0 or not. So if you don't set it to 0, your representation remains an ordinary Werner module. But if you set it to 0, you get a degenerate representation whose primary field is called the degenerate field, and it obeys this null vector equation, meaning that a specific descendant here, that's a creation operator, vanishes. Okay, so then we made things depend on Z to get field. So by the state field correspondence. But fields have a very specific dependence on Z given by this axiom here. And this implied in particular that we could build a field called the energy momentum tensor, T of Y, which in fact doesn't depend on Z. That's why it's only a function of Y. And this is a convenient way to enforce a conformal symmetry in OPEs or correlation functions. And to do that, we use the operator product expansion of T of Y with a primary field here. And this operator product expansion is essentially equivalent to the definition of the primary field. Which, let me remind you here, so primary field V delta, it obeys ln strictly positive V delta is 0 and L0 V delta equals delta V delta. And so we have started working out the consequences of conformal symmetry for operator product expansion. And we have already found how the coefficients depend on the coefficients, but we'll go further and try to show that the contributions of descendants are completely fixed by the contributions of primary. So let's go back to this operator product expansion, V delta 1 Z1, V delta 2 Z2. And we focus on contributions from a primary field and its descendants. So we sum over creation modes. We have some coefficients here, some OP coefficient. And then we have an arbitrary descendant, LV delta of Z2, with L1, L minus 1. So L is the set of creation modes. So the idea to derive constraints from conformal symmetry was to insert on both sides of the OPE an expression built from the energy momentum tensor. So we insert 1 over 2 pi I, integral around Z1 and Z2 of dy, y minus Z2, L plus 1, T of y. So inserting it on the left-hand side, we could close the contours around the field. Delta 1 and V delta 2, and using this OPE here, we just computed the following left-hand side. So we had ln acting on the field at Z2 plus Z12 to the n plus 1 VZ1 plus n plus 1 Z12 to the n delta 1. So V delta 1 V1, V delta 2, Z2. On the other hand, on the right-hand side, we only have a field at Z2. There is nothing at Z1. And this gave us just the action of ln on all these fields. Okay, so we use this equation in the two cases n equals -1 and n equals 0. And this gave us the dependence of the OPE coefficient here on Z1 and Z2, which was Z12, the delta plus L, the level, minus delta 1 minus delta 2. Okay, and then we still have some coefficient, C delta L, delta 1, delta 2, which is now a constant. So we can now focus on n greater than 1. Already this makes a small simplification because here ln acting on the field V delta 2 vanishes because it's a primary field. And then we can just act. I mean, we can use again the OPE here, but we can act with this dz1 and the OPE coefficient now that we know how it depends on z1. So the left-hand side becomes a bit simpler. It becomes the sum of this coefficient, now this constant coefficient, times z12 L plus n. Then we have a term delta plus L plus n delta 1 minus delta 2, L v delta of z2. And here I'm forgetting a prefactor, which is just a z12 to the delta minus delta 1 minus delta 2. And that's supposed to be equal to our right-hand side. The right-hand side, which is just here, which also has the same prefactor now. Delta minus delta 1 minus delta 2 times sum. Well, let me put the ln here. ln z2, of course, acting on sum c delta L delta 1 delta 2 L v delta z2. And there is a z12 to the L. Okay, so this may look a bit complicated now, but we'll simplify it and focus on examples. So first, this prefactor is the same on both sides, so that's one thing. And then, if you want, both these terms are a series in powers of z12. So they should agree. They should agree degree by degree in z12. So let's focus on the term z12 to the n for some big n. So if we do that, we get the following equation. So we get here we get this overall factor. Now that we fixed, we have to fix the level L. We have, so in this term we have to fix L equals n minus n. So we get delta plus n minus n plus n delta 1 minus delta 2. Then a sum over not all dissonance, but all dissonance at the correct level. C delta L delta 1 delta 2 L v delta T delta equal. So on the right hand side, it's ln acting on a sum at the level n now. T delta L delta 1 delta 2 L v delta. Okay, so basically we get an equation which tells us what happens if we act with ln on this combination of states at a given level. And the coefficients now are the OPE coefficients. So the claim is that using this equation, we can deduce all the OPE coefficients of dissonance from the OPE coefficients of primaries. And I want to illustrate this claim in examples. But are there questions up to now? So let's focus on the special case n equals 1 and small n equals 1. Then we have delta plus delta 1 minus delta 2. So here I'm rewriting this thing. Sorry, small change of notation. I want to focus on a solution of this system. So this is the known. I want to focus on a solution such that, well, I will call F this solution. And this solution I define by saying that the primary state has coefficient 1. So, let me come back to the special case. N big N equals small n equals 1. So here I have a sum only at level 0. So its coefficient here is precisely the one which are normalized here. And so we get delta equals, and then the right-hand side is a L1 acting on, well, some F L minus 1, L minus 1 V delta. So this starts to be really simple. And, well, we have to commute L1 past L minus 1. So that's just F L minus 1 delta V delta.
Is the same thing as C? What was S?
Yeah. S now is the new name of C. Or if you want, I'm writing, it's a choice of formulation. So I'm writing C delta L delta 1 delta 2 as some C delta delta 1 delta 2 times F L. So F delta L delta 1 delta 2 with where F obeys this condition.
So should it then be F0, the upper, because the primary is level being 0, right?
No, but this here in my notation is the creation operator itself. So if you want here, I have the creation operator 1, which has level 0 indeed. So I have written, but probably erased the list of creation operators. So I had this list which was 1, L minus 1, L minus 1 squared. So 1 is the first creation. Well, it doesn't create much, but okay. It has level 0. Okay, if you can admit this notation. Okay.
I'll get used to it.
Well, I won't use it too much. Okay, so now let's solve this equation. So, well, this is a rather simple equation, right? Which gives me FL minus 1. So the coefficient of the first non-trivial term in the OP is now, well, delta plus delta 1 minus delta 2 over 2 delta. It has a pole at delta equals 0, and, well, that's not a coincidence. Delta equals 0 corresponds to delta 1, 1, the dimension for which we have a singular vector at level 1. And of course, that's because here we obtain L1 acting on some vector at level 1. And the vanishing of this action is by definition the condition for having a singular vector. Okay, so let's push the calculation to level 2. I promise I stop at level 2. So the claim is still that I can determine uniquely the OP coefficient here. So I have to consider the N big N equals 2 in this equation. And so the first thing I can do is small n equals 2. So we get delta plus 2 delta 1 minus delta 2. So here it's again a sum at level 0. So we again get just delta equals L2 acting on, well, acting on some W, where I define W as my vector at level 2. So it's an arbitrary descendant at level 2, but with coefficients given by the OP structure constants. And then for n equals 1, we get, well, delta plus 1 plus delta 1 minus delta 2. So here we have to take a level 1 descendant. So that's f l minus 1 l minus 1 delta equals L1 acting on W. So we get the system. We get the system of two equations, which, if you write them explicitly, amount to linear equations for these coefficients, fl-1 squared and fl-2. The left-hand side is known because this fl-1 we already determined. So by solving this system, you can compute fl-1 squared and fl-2. Now you see, if you had 0 on the left-hand side, your system would just be the condition for W to be a singular vector at level 2. So again, the system becomes non-invertible if you have a singular vector, which means if delta is either delta 2, 1 or delta 1, 2. And yeah, we'll see soon what it means. Okay, but for the moment, let's accept that this pattern goes on to higher levels, and that you can determine this OP coefficients f uniquely by solving these word identities. So we can rewrite the operator product expansion now. It's just v delta 1 v1, v delta 2 v2 equals, so well, rather it contains the following term. So we have an overall structure constant here. We have v dependence. And then we have our primary field, v delta v2. And then the contributions of all the descendants, which are of the type sum, L, some creation operator, which is not 1. And then the coefficient v1 to the n, and the coefficient f delta L, delta 1, delta 2, L, v delta of v2. So here we have this basis of descendants with some coefficients which we know. And therefore, if you know this term, if you know the primary field with its coefficient, then in principle you know all the rest. So, well, one remark is that this justifies our focus on highest weight representations with the idea that the conformal dimension should be bounded from below. Because now we have a sum of, we have a series in powers of z1, 2 with increasing powers. And if z1 is close to z2, I mean, this series could converge. If, on the other hand, we allowed levels which were negative, well, infinitely negative, then it would have trouble to converge near z1 equals z2. So that's, if you want, a technical justification for this highest weight representations. So other questions? Okay, so then a quick warning. I mean, this idea that descendants are completely determined by primaries, I mean, this works with the Virasoro algebra, but does not necessarily work with in other situations, in particular the W algebra.
What is the property that is missing that works with Virasoro and doesn't work with general W algebra?
Well, the point is that we need to have enough word identities to determine these quantities. And if you do the same exercise for W algebra, you won't necessarily get enough equations. So it will remain some freedom, and you could have several solutions to our linear system, which you can interpret as having a fusion multiplicity.
It's the space of solutions always finite dimensional for W algebras. That's the equals all part.
No, it's not even finite dimensional. well, I mean, it depends on the case, right? But in general, it's not. Okay, so now I'd like to focus a bit more on what happens when we have degenerate fields or degenerate dimensions. So what if the delta here belongs to delta RS? And as we saw in the case of level 1, then we get a coefficient here which has a pole. This coefficient here has a pole at delta equals 0. And that's true also for higher levels. For example, at level 2, well, the coefficient also has a pole if the dimensions are degenerate. So what do these poles mean? So let's focus on the case delta equals 0 to begin with. Well, the simple interpretation is that the pole means we have a wrong normalization condition. So we wanted the coefficient of the primary to be 1, but that's not possible. Instead, we should put the coefficient of the primary to be 0 now. And then maybe it's the coefficient of the first descendant, which should be 1. So the outcome is that you get an OPE, which instead of starting with the primary V0, so let me write it. So V delta 1, V delta 2. So I'm writing just the fields now. So instead of having V0, you start at L minus 1 V0. And then you have the descendants of that field, which, if you want, is the same as a V1, the primary field of dimension 1. So the interpretation is that, well, this module of dimension 0 appears, but only some of the fields in the module contribute to this OP. Okay, so now what if I'm looking for a degenerate field in this OP? So the question is whether V11 can belong to this OP. So V11, by definition, has a vanishing null vector here. So L minus 1, V11 degenerate is 0. So we can't really say that we normalize the OPE with the coefficient of this vector because it's 0. So we are forced, in fact, to have f L minus 1 equals 0. So if we go back to our equation, which determines that L minus 1 here, so the equation here, this was, well, this right-hand side, now it must be 0. Fl minus 1 is 0, delta is 0, that's 0. So we are getting just delta plus delta 1 minus delta 2 equals 0, which, well, delta being 0 means just delta 1 equals delta 2. And therefore, this degenerate field can appear in the OPE only if delta 1 equals delta 2. So now there is a related exercise you could do, which is to consider the OPs of some field of dimension 0. So if we put delta 1 equals 0 in the general operator product expansion, so, well, if you do that, actually nothing happens. Really, you can take all the formulas. That's just a special case. On the other hand, if you want to put a degenerate field in the OPE, well, something must happen because you have to satisfy the null vector equation here. And so let's write this OPE. What we know already on this OPE is that it has Z12 to the power delta minus delta 2 times, well, some V delta plus descendants. But then I have to assume D by dV1 is 0, acting on this field, and therefore acting on this OPE. V by VD1 must be 0, and I get delta equals delta 2. In other words, if D11 V delta 2, well, is only the only primary field that can appear is V delta 2, which is consistent with the claim that this degenerate field is proportional to the identity.
There could be some other field with the same dimension. As long as the dimension.
Right. So this field is not forced to be the identity. It behaves, yeah, like the identity. But if you have several fields with the same dimension, some things could happen. Okay, so now what we are discovering is called fusion rules. So fusion rules are constraints on operator product expansions that follow from the existence from the vanishing of non-vectors if you have degenerate fields. And here we have, if you want, two different ways to write the same fusion rule for the degenerate field at level 1. So it's convenient to write these rules in terms of a fusion product of representations. So the idea is that there exists a fusion product of representation of the Virasoro algebra, which is, if you want, a kind of generalization of the tensor product. It's a bit different from the tensor product. In particular, if you were doing tensor products, the central charges would add, whereas here we work at the fixed tensor. So the fusion product, well, the interpretation in terms of a fusion product here is that the degenerate representation are D11, to which this field belongs. If you take a product with a Verma module here, to which this other field belongs, you find just the Verma module. And the interpretation of this fusion rule here in terms of a fusion product is that R11 belongs to the fusion product V delta 1 times V delta 2. Well, that's possible only if delta 1 equals delta 2. I won't construct the fusion product. I mean, it has an algebraic construction. But the nice thing is that then it is associative and commutative. And we use this associativity and commutativity to compute higher fusion products. So let me rewrite these statements in an even more algebraic way. I mean, in a sense, these are two dual statements, and one way to write them is the following. So one way to write this statement in particular is that in terms of the homomorphisms from V delta 1 times V delta 2 to R11. So by homomorphism, I mean a linear map that commutes with the action of Virasoro symmetry. And the point is that the dimension of the space of homomorphisms is just delta 1, delta 2. So it's 1 if the two dimensions are equal, and otherwise it's 0. Okay, and then the equivalence between these two statements, well, I can write it as the space of homomorphisms from R to R prime for any two representations R and R prime of Virasoro is isomorphic to the space of homomorphisms from R times R prime to R11. Okay, so that's just the algebraic interpretation of this rather trivial fusion rule. So let's now consider less trivial fusion rules, unless we have questions.
You mentioned this fusion product as associative and commutative. Is that obvious from the manipulations you do to derive these rules, or is it something you're going to show? Or
the answers are no and no. No, it's not obvious, and I won't show it.
But what is it algebraic? Is it an actually, is it a product? Or what is it?
Yeah, it's a kind of bilinear product. What makes it complicated is that to write it, you need to introduce the positions Z1 and Z2. So a bit like in my calculation of OPs, I have Z1 and Z2 dependence, which eventually got eliminated. I mean, the product at the end doesn't depend on Z1 and Z2, but you cannot really write it without introducing these positions.
Well, it's not well defined on any. Like it's not really a bilinear product because you cannot multiply two primaries together. That would give you infinite different
Yeah, you're worrying that we could get an infinite sum of vector spaces.
I meant that if you take a product of two primaries, like Z1 equal to Z2 equals 0, then the right-hand side is infinite because there's a Z1 minus Z2.
Ah, right. Thank you. I understand. Yeah, right. You have to introduce different positions because if you try to do everything at the same position, it will indeed diverge.
But there can be an infinite. Nothing prevents delta 1, delta 2 to be infinite.
Yeah, right. So in principle, the product of two representations can give you an infinite sum of representations. Although I guess in most algebraic frameworks, you want to forbid that and focus on the rational theories where you have only finites.
The operator product expansion of fields in quantum field theory is associative and commutative. The operator product expansion.
Yeah, the operator product expansion is indeed associative and commutative, but the difference is that the operator product expansion comes with some coefficients here, this C here, which can be just any numbers. But in the fusion product, the coefficients are integrals because it's just, well, just like in a tensor product. It's an algebraic construction with integral coefficients. So that's really a non-trivial statement. Okay, so let's compute fusion products of degenerate representations, and we can start with a degenerate field VD21, which is degenerate at level 2. So what are the constraints for VD21 belonging to operator product V delta 1, V delta 2? Well, you see, if we set delta to be delta 21 here in this system, well, the system becomes of rank 1, and therefore it won't have, in general, a solution, except if the left-hand side of the system, if these numbers here obey some constraint. And this constraint, well, this constraint is the following. I mean, you can really derive it from this equation if you expand it more explicitly. So that's delta 21 plus 2 delta 1 minus delta 2. So here you recognize this coefficient here with delta equals delta 21. And that must be equal to 3 delta 21 plus delta 1 minus delta 2 times delta 21 plus 1 plus delta 1 minus delta 2. Where here you recognize this coefficient. Okay, so what are the solutions of this system? So here we need good notations. Again, I mean, this is already getting complicated. And we already introduced the good notations, which are the momentum P instead of the dimension delta. So at the time, you may have thought that it was an overkill because, I mean, just introducing P in order to simplify the formula for delta RS, I mean, it's not such a big simplification. But now, if you introduce momentums in this equation, well, what do you get? You get just this statement, product beta over 2 plus or minus P1 plus or minus P2 equals 0. So, what's the outcome? Is that the degenerate field can belong to this product, to this OP. Now, let me use the momentum, P1 to P2, well, provided P1 is P2 plus or minus beta over T. A modulo the reflection of momentum P goes to minus P, and P and minus P are equivalent. And then using this duality between the appearance of the degenerate field and the fusion product of the degenerate field, I mean, this is equivalent to VD VP. It gives you just two possible primary fields with momentum P plus or minus beta V. If you had done it for V1, 2, you would have found what? Anyone has an idea? Yeah, one of the beta. These two fields are related by inverting beta, as you can see more or less in this formula as well. So these fusion products are really essential for solving CFTs. I mean, they are really the basis, the technical basis for most of what we'll do in this course. I mean, the fact that we have fields with OP gives a finite sum of other primary fields. I mean, that's a statement which not only helps us build CFTs like minimal models where you have finitely many fields in the spectrum, but it also constrains CFTs like Liouville theory where you have infinite spectrum.
It's literally very much like spin 1/2 and so forth.
Yeah, it's very much like spin 1/2.
The number of elements you're summing over on the left-hand side is, and the right-hand side is proportional to the level?
Yeah, it is the level. It's because it's level 2.
Right.
I'm going to make a more general statement about that. Because now we want from this to deduce, we want to deduce the existence and fusion products of all other degenerate fields. Because, I mean, I told you how we could derive this existence of degenerate fields at level 2 by doing just, by looking for null vectors at level 2, but then I stopped there. I never looked at null vectors at level 3, 4, etc. And it would be very tedious. But now the claim is that I can get these results, and in particular this formula, from here. So how do I do that? Well, the big statement is that a representation is degenerate level n if and only if its fusion product with some Fermat module is a sum of n terms, which I don't specify. So I want to replace the algebraic characterization of having vanishing null vectors here inside the representation by a statement about, if you want, the category of representations, or equivalently about fusion product. So let me give a rough argument why this equivalence holds. So if you have a degenerate vanishing null vector at level n, then even without doing the calculation, if you write the systems we wrote at level 2, you'll see you have to get some polynomial equation for delta 1 and delta 2. And if you look, even without doing the calculation, but if you look at the degree of this polynomial, you'll find it's a degree n polynomial. One way to write this equation is to say that the residue f delta L, delta 1, delta 2, you want this residue to vanish. So you can compute this for generic delta, but now if you want to study some degenerate value of delta, you find it has some pole and you want the residue to vanish. And this gives you your polynomial equation of degree n. And so by solving this polynomial, you get n terms here. On the other hand, if your representation is not degenerate, if you don't have any null vector, in fact, well, the point is that you don't get any constraints because your system of linear equations for the OP equations has a unique solution. So, so that's it. Then you can have basically any Verma module appearing in the OP.
Less than n?
No, infinitely many, anything, right? There is no constraint. Yeah. So now, I mean, armed with this claim, let's say, I wouldn't say theorem or even reason. At least we have an argument for it. So let's consider, for example, the fusion product of R21 with R21. So two degenerate representations here. I'm omitting the in superscript D. So first, we know that an application of this fusion rules, basically, what we expect are two representations whose momentums are P21 plus beta over 2 and P21 minus beta over 2, which is the same as P31 and P11. Now the question is whether these are Verma modules or degenerate representations. To do that, to answer this question, we can consider R21 times R21 times VP. We can consider this fusion product, and now it's associative. So what does it mean? Well, it means I can compute it this way. So first I do this OP, and then, well, this product. So if I do that, well, I'll get something like V. Well, not something like, I'll get exactly V minus beta plus 2P plus VP plus beta. This is just iterating my fusion rule here. On the other hand, I can do it like that, where I have here my two representations, VP1 plus VP11 times VP. But now, this product gives me finitely many terms. And by this general idea, this implies that these representations have in fact to be degenerate. And so this module, if it's degenerate, it means it's just R11. And from this, you can deduce that this is also degenerate. You can deduce its fusion product. So let's call it R31 now. Well, here you get VP minus beta plus VP plus VP plus beta. And since you have three terms, it degenerates at level 3. So without having to really compute the singular vector, we have found that that this one has vanishing null vector at level 3, and we have found its conformal dimension given still by this formula. And then you can iterate. And the statement is that you have an RRS where you have this, for example, if you do a fusion product like that, you get two terms which are just R plus or minus 1S. R12 helps you iterate the second index. And then by recursion and R and S, you can get, well, you can get the fusion product of this one with any Verma module, which is just the sum I equals minus R minus 1 over 2, R minus 1 over 2, J minus S minus 1 over 2, S minus 1 over 2, Vp plus I beta plus beta minus 1. So here the sums run by integer increments, I mean increments of 1. And this tells you have R times S terms in these sums. As you would expect for a degenerate representation with additional vectors element Rs. And you can also compute the fusion products of degenerate representations among themselves, which is R1 S1 times R2 S2 equals sum R equals R1 minus R2 plus 1, R1 plus R2 minus 1, S equals S1 minus S2 plus 1, S1 plus S2 minus 1. Here the sums run by increments of 2, and that's R. Okay, are there questions?
What's the number of terms now? It's smaller than the product.
Yes, the number of terms, you're right, it is smaller because you have several vectors on the left, basically. So you have to take the intersection of what you would expect from the constraints from this field and the constraints from this field. So this correspondence between the level and the number of terms is really valid if you do a fusion with a Verma module. But if you start mixing the degenerate representations with one another, yeah, you have this subtlety. Okay, any more questions? So if not, I think we're ready to look at correlation functions. So correlation functions are really the essential object. They are the observables, if you want. They are the objects which we want to compute to experiments. For example, in the Potts model, you have a special class of correlation functions which are connectivities and which tell you the probabilities that some points belong to the same cluster. So if you do some type of calculation here, let's say you have 5 points and you wonder if the percolation relates all these points, if they belong to the same cluster, and that will correspond to some 5-point correlation function, basically in the conformal field theory. So we will focus on correlation functions on the sphere. So there are other observables like correlation functions on the torus, on other Riemann surfaces, on surfaces with boundaries. You even could define entanglement entropy, but these are all only observables in this course.
So in the OP of two dimensional fields, what are the indices running? It's R squared equals?
No, it's R equals, and this 2 means
in increments of 2.
Increments of 2. So you start here and you add 2, etc. Okay, so the correlation functions are the real thing in contrast to fields themselves, for example. I mean, fields are not an object fields are just a device to help you compute correlation functions. So all the relations we have written about fields, they are supposed to be true inside correlation functions, because a correlation function is, if you want, the expectation value of a product of fields. So that's the endpoint function. And the basic principle is that it depends linearly on fields. So if you want to take a derivative of a correlation function with respect to Z1, well, it's the same as taking the derivative of the field.
I have a question. Are you going to discuss contact terms?
Contact terms. No, I'm not going to discuss contact terms. So
Are they important, non-important?
No, so in my operator product expansions, I always assume the fields do not coincide. And
In general, we want to get into relation function. So it depends what you call relation function. In general, you come to terms, which sort of cases are really important if you want to.
yeah, I mean, I think they may be important if you want, in particular, to integrate correlation functions as you would do for some applications like string theory. But here, I don't want to integrate them. I mean, I have more like statistical physics in mind. And in this type of applications, you don't need to look at coincident fields. Okay, so let's compute correlation functions, and let's start with the constraints from conformal symmetry. So just like for operator product expansions, the right tool to derive these constraints is the energy momentum tensor. So let's assume we want to study the correlation function, this n-point function, product d delta I of di of n primary fields. Let me define z of y at the same thing with an insertion of t of y. And then we want to study the properties of z of y and deduce how z behaves in the conformal transformations. So this z of y, I mean, its properties are determined by the OPE of t with primary fields, which I write here. T of y v delta of z is delta over y minus z squared plus y 1 over y minus z d z v delta of z plus regular terms. So this tells you that z of y is, well, it's meromorphic and it has double poles whenever y is equal to some zi. And you know some things about the residue of these poles. But to completely determine z of y, you also need to know what happens at y equals infinity. Now, I mean, we assume we live on the Riemann sphere. So infinity is just one point like any other point. It can be, you can exchange it with another point by some conformal transformation. So nothing special should happen at infinity. And the field should be, in a sense, regular at infinity, unless there is a field at infinity, which I don't assume for the moment. So, in particular, the energy momentum tensor, well, we need some conditions telling us how it behaves at infinity. And now I'm accepting that the right condition is that it behaves at order 1 over y to the 4th. Well, we'll check in a few minutes that this is at least consistent.
Is somehow dimension 2.
Yeah. Yeah, right. That's the argument, indeed. But we'll see that shortly. So if we know that, we can actually compute z of y, because, well, we have all these poles and their residues. So we have this sum of delta I over y minus zi squared plus 1 over y minus zi v by dzi acting on z. And that must be the answer, because I mean, you have the correct poles, you have the correct residues, and you have a z which decreases at infinity. So this is enough to characterize z as a meromorphic function on the Riemann sphere.
This is really due to the fact that no, this is just because it's regular at infinity. It doesn't use the property of t.
Right. So I'm using only the fact that t decreases at infinity. I'm not using the full assumption that it decreases that fast. And that's why I'm going to use next, because it will give me extra constraint on z. So I really want t to decrease as 1 over y fourth, so z of y also should be of order 1 over y fourth. And in particular, the terms of order y minus 1, well, they have to vanish. What are these terms? Well, this term is sum d by ddi z equals 0. What is this equation called?
Translation invariant.
Yes, translation invariance. So we have done all this to rederive just translation invariance. Well, okay, we'll derive things that are not so trivial. So, order y to the minus 2, well, sum zi d by dzi plus delta I, z is 0. Well, that's called dilation. Well, not really invariance, dilation covariance. I mean, invariance would be if I didn't have this term, that I have a contribution here depending on conformal dimensions. And then order y to the minus 3, sum of zi squared d by dzi plus 2 delta I zi is 0. And so these three equations are the global Ward identities. And they tell you how our correlation function behaves under a global conformal transformation. Well, they are the infinitesimal version of the global conformal transformation. So,
I mean, you assume Z is holomorphic in ZI or?
no, I'm not assuming this.
Because
The object which is holomorphic is T, really, T of Y. The Z, for the moment, it's not necessarily holomorphic. I'm just assuming it is differentiable.
Z bar dependence.
Well, we'll see that later. I'm keeping safe, I'm staying safely in chiral CFT as long as I can. But I mean, very soon I'd have to move to non-chiral CFT. Okay, so these are, if you want, infinitesimal translations or dilations, but there is a finite version of these equations. So they are really equivalent to the following equation about the global conformal transformations, which is that if you change zi by a zi plus b over c zi plus d, so this is SL2C transformation, well, you get the same correlation function times the prefactor product I equals 1 to n c zi plus d to the 2 delta I. Okay, so in particular, we can use this type of transformation, maybe z goes to 1 over z, to map the point at infinity to a point at 0. And if you do that, you'll find that any primary field, v delta, when z goes to infinity, well, it has to be of order z to the minus 2 delta. Or in other words, you can define the limit of z to the 2 delta v delta of z. And let's call that v delta at infinity. And if you apply this indeed to the energy momentum tensor T itself, well, if you remember, T is a field of conformal dimension 2, and therefore, by this equation, well, we recover T being of order y minus 4. Okay, there is a small subtlety here. I mean, is T really a primary field? So if you look at its operator product expansion, T of y, T of z, you find C over 2 over y minus z to the fourth, plus 2T of z over y minus z squared, plus the rest. So basically, if I didn't have this term, T would be a primary field of conformal dimension 2, because we have a coefficient 2 here. But I have this term. The point is that T is still a quasi-primary, so a primary field, but only for the global symmetry, meaning that it is filled by L1 And of course, it is an eigenvector of L0. So that's the definition of a quasi-primary field of dimension 2. And to have a true Virasoro primary field, you also need it to be filled by Ln, starting with L2. But these conditions are actually not needed for deriving these global world identities.
The blackboard because it's wrong.
Sorry?
You shouldn't leave it on the blackboard because it's wrong.
This equation is wrong.
Yes.
Yeah. Okay. Right. Well, I already wrote 1 equals 0, so basically, I mean.
Okay, absolute value of 1.
Okay. Okay, so now, if we agree with this global world identity, well, we have to solve them to determine the correlation functions, and I think we'll do that after the break.
Maybe questions?
Yeah, other questions?
Yeah, can. So, but the way you derived it, it was slightly circular, right? Because you assume that t decays like 1 over y to the 4 to derive this transformation of correlation function, and then you showed that's consistent with t decaying like 1 over y to the 4. So that's still.
Yeah. Yeah, that's what is nice with an axiomatic approach. So I can assume anything, and then so long it doesn't crash it down, I mean, I'm okay. So indeed, I would be happy to know a simple derivation from first principle, but I'm not sure it's even possible.
Of this all.
Hmm?
Simple derivation.
Of the fact that t decays as y to the fourth, 1 over y to the fourth. I mean, we have to say that there is no field at infinity, because as soon as you put some field at infinity, t may not decay at all. I mean, it may be singular at infinity. So you have to formulate the absence of field at infinity in some way. But it's hard to do it before even deriving the conformal transformation, which can map infinity to some finite point.
So this means really this OP, they are really for the sphere. I mean, they will change it, they change themselves.
No, okay. The OP was something very local, so it would apply on any Riemann surface. But these global world identities, yes, they are only for the sphere. With solution of the global world identities. And let's start with the simple case of 1-point function. So now z is just some v delta of z. Now this 1-point function has to obey these 3 identities, which boil down to just d by dz is delta equals 0. And if you want your correlation function to be non-zero, you need delta to be 0. So your 1-point function, well, the solution is that it has to be proportional to a delta function, that the dimension should be 0. Well, that's why 1-point functions on the sphere are not terribly interesting. So let's consider 2-point functions. Well, that's some v delta 1 z1, v delta 2 z2. So here we have 3 world identities, but only 2 variables, z1, z2. So again, the solution can be non-zero only if you obey some condition, if the dimensions obey some condition, and if you work out this equation, you find the condition that the 2 dimensions have to be equal, in which case this 2-point function becomes z1 minus z2 to the minus 2 delta 1. Now, a 3-point function. So for a 3-point function, you have as many equations as variables, z1, z2, z3. So there is generically a solution, a unique solution, basically, up to a constant for any values of delta 1, delta 2, delta 3. And this solution is, well, Z12 to the delta 3 minus delta 1 minus delta 2, Z23 delta 1 minus delta 2 minus delta 3, Z13 delta 2 minus delta 1 minus delta 3. Now, 4-point function. Where should I stop actually? Well, I think I'll stop here at the 4-point function. Now we don't have enough equations basically. The 3 word identities, if you want to determine how this 4-point function depends on 3 of the 4 variables, but you're left with one free variable. So the way you, the solution is, well, somewhat complicated. So we have a bunch of prefactors, Z13 to the minus 2 delta 1, Z23 delta 1 minus delta 2 minus delta 3 plus delta 4, times Z24 minus delta 1 minus delta 2 plus delta 3 plus delta 4, minus delta 4, Z34 delta 1 plus delta 2, minus delta 3 minus delta 4. And you're left with an arbitrary function, now G. It's not just a constant, it's a function of a combination called the cross ratio, Z12, Z34 over Z13, Z24. So the cross ratio. Okay, so a bunch of powers of differences of positions times an arbitrary function of the cross ratio. So 4-point functions are.
Cross ratio is invariant.
Yeah, exactly. So the cross ratio is a combination that is invariant under this global conformal transformation. So let me call x the cross ratio. So that x goes to x under this transformation. Okay, so 4-point functions are really non-trivial. They are really functions instead of just being a constant times some universal function of C. Now, there is one nice way to rewrite this if you fix the points Z2, Z3, Z4 to be 0, infinity, and 1. In which case, your 4-point function, so V delta 1 of V, V delta 2 of 0, the V delta 3 of infinity, V delta 4 of 1, well, it's just G of V. So if you want this G, this function can be interpreted as a special 4-point function with particular values of the positions. Oops. Do I really want to erase all this? No. Not yet. So this is what I want to say on the global word identities and the consequences of these identities for correlation functions. But I still have to show, as I did for the OPE, that I can determine correlation functions of descendants from correlation functions of primaries. This is again a consequence of conformal symmetry, but this will be a consequence of the so-called local word identities. So this Z of Y is still very useful to derive local word identities. And to do that, I can compute the integral around Z1, let's say, of 1 minus Y over Y minus Z1 to the N minus 1 times Z of Y. So I have two ways to compute this. So either I'm closing the contour around Z1, in which case I have to use the OPE of T of Y with V of D1. So let me remind you that this V of Y, I mean, that was T of Y, V delta of D1, etc. So if I'm using this OPE, well, by design, I will find L minus N acting on the first field times all the other fields. basically I have just arranged to pick the contribution of L minus N in the OPE by having this prefactor. So that's basically a descendant. On the other hand, I'm on the sphere. So here I have a contour around Z1, but that's the same as taking the sum of contours around all the other positions of the other fields. And if I do that, I rewrite the same quantity as a sum, J equals to N. And then again, I have to use the OPE of T, but with the other fields. Now my prefactor is perfectly regular at this position. So it's just a simple calculation of complex analysis. And the result is minus 1 over Vj1 n minus 1 T by Tj plus n minus 1 over Vj1 to the n delta j times, well, my original correlation function, product d delta I and di. And so I get this local word identity, which expresses how a descendant is a differential operator acting on the primary correlation function. And this works here for a simple descendant with only one creation operator, but I could have a product of creation operators, and the same calculation would lead you also to an expression in terms of the primary correlation function. So that's why we so often neglect primaries. And they are taken care of by conformal symmetry. Descendants, sorry, thank you. Okay, any questions about these word identities? Okay, so if not, it's time to leave the.
What would you do if you had a correlation function of multiple descendants, but then the argument?
Yeah, you do exactly the same, but it becomes more complicated because I mean, if here I had some other descendants, that would change the operator product expansion of the T of Y with these fields. So I would have to keep more terms in the OPE. I would get a bunch of things, which it would still be a big differential operator, but much more complicated. Okay. So now, that was all what we've been doing is chiral conformal field theory. We had just one Virasoro algebra, and everything was holomorphic, basically, or meromorphic. But that's not how the real world is. So the real world is not really holomorphic. And in particular, we have functions of the type z to some power delta. But correlation functions in the real world, they have to be single valued. You don't want to have branch cuts. And if delta is not integer, this function, well, it's not really well defined. So the functions we would want to have are of the type z to the delta, z bar to the delta bar. So now there is a big subtlety with the notations here. I mean, z bar for me is always a complex conjugate of z. So it's really a function of z. It's not independent from z, of course. On the other hand, delta bar is just some number which does not have anything to do with delta. So if you allow functions like that, I mean, it's easier to build non-trivial correlation functions because for that to be single valued, you only need delta minus delta bar to be integer. And this perfectly makes sense. So we have to worry a bit about functions of this type, and we have to revise what we said about conformal transformations, basically. So I was saying that the generator of a conformal transformation is minus z to the n plus 1 d by dz. But that's true only if I act on holomorphic functions, basically. If I act on a general function, the correct generators of conformal transformations, they involve also ln bar, which is just minus Cn plus 1 by dz bar. So in fact, to be precise, the generators are ln plus ln bar and li ln minus ln bar. So this is really the conformal algebra, acting on general functions on the sphere. No, I don't want just to act on functions. I want to act on my space of states, which is a complex vector space. So I can combine these with arbitrary complex coefficients. So basically, I get two algebras which commute ln and ln bar. So the Vit times Vit algebra. And then if I do the central extension to get the Virasoro algebra, well, we get the conformal algebra. Well, okay, I call that the conformal algebra, but probably what I really want to call the conformal algebra is after central extension, and that's Virasoro times Virasoro, which I note with a bar just to say it's the right one. So I have the left Virasoro and the right Virasoro. I'm assuming they have the same central charge for simplicity.
Why don't you call a width bar also?
Yeah, I should call it Vit bar. Yeah, I should distinguish it.
But if you identify Z bar as complex conjugate of Z, do you really have two copies? You just have like the one subgroup of it, right? If you don't keep Z and Z bar independent. It's only when they're independent that you really have two copies, no?
Yeah, so it depends on what space I act. But if I'm acting on a complex space of states, or even a space of complex functions on the sphere, I mean, in fact, I can take arbitrary complex coefficients of these generators and I get two independent copies. It's a bit like, I mean, our space, let's say our algebra of global conformal transformations, they live in SL2C, the Lie algebra SL2C. But if you want, that's a six-dimensional real Lie algebra. But then if you act on a complex space, you have to complexify it. And what is the complexified of this algebra? Well, it's in fact SL2C times SL2C.
But at the end of the day, even in this example, you would go to the section where the Z bar is Z star, so that would again get you back to the SL2C, right? It's not like you have, I mean, it's, yeah. Only when you analytically continue that you actually have this product, right?
Okay.
I mean, okay, maybe the way I'd say it is you're implicitly assuming Z bar is independent of Z when you're doing this, and then in your mind, I mean, at the back of the mind, it's that they're identified. So, but okay, thanks.
Okay, I mean, we'll see exactly how Z bar and Z are related when we look at shortly correlation functions, and we want them to be single valued, a bit like this argument. Right? So SL2C complexified is SL2C times SL2C.
Sorry, in your axiomatic approach, why the C of Virasoro bar should be equal to the central charge of the Virasoro?
Yeah, to make our life simpler. But I mean, I don't think we are obliged to do that. But I will only talk about CFTs with the same central charge on left and right, and I'm not sure, I mean, if you have anything interesting, if they differ.
I mean, that do not exist.
I'm not sure, actually.
Okay.
There are interesting examples where they are not the same. For example, your holomorphic CFTs, you can think of them as CFTs that have a right central charge 0 and left central charge non-zero. For example, monster CFT.
Well, yeah, I mean, it's literally a good example because at any central charge, you can have a trivial CFT with just the identity if you want. So I mean, is the central charge of your trivial CFT really well defined? Well, okay. Maybe that's not really.
There are probably other examples which are less trivial on the right.
Yeah. Yeah, thank you. So, yes. Anyway, there's nothing against having different central charges except simplicity. So now we have a right-moving Virasoro algebra. We have to do everything with it that we did with the left-moving. So, for example, we have a T bar, which is a sum of ln bar over y bar minus t bar n plus 2. So T bar of y, I'm writing it as T bar of y because y bar is after all a function of y. But this T bar of y obeys dy T bar of y is 0. On the other hand, T of y obeys dy bar is 0. So these are the left and right energy momentum tensors. And now when I have a field has a left and right conformal dimension. So a primary field, V delta bar, well, that's the left conformal dimension, right conformal dimension, and the spin, the conformal spin is defined as the difference of the two dimensions. Okay, so what happens to correlation functions now? I mean, the correlation functions, they have to obey the constraints from the left and the right conformal algebras, well, Virasoro algebras. So let me introduce a notation. So when I have a function which depends on positions and conformal dimensions, modulus squared means this, f times f of delta bar z bar. Where again, delta bar is some variable independent from delta, and z bar is the complex conjugate of z. So if I look at the two-point function in particular, so now I write v1, z1, z2, z3. Well, they are still primary fields, but for simplicity, I can parameterize them with indices. So this two-point function, well, it should be basically the modulus squared of what we had, which is erased, but it's the delta 1, delta 2, z1, 2 to the minus 2 delta 1, modulus squared. Up to some constant factor, which I call v1, 2. So that's the two-point structure constant. And similarly, for a three-point function, v1, v1, v2, v2, v3, v3, we get a three-point structure constant c1 to 3 times the v1, 2 to the delta 3 minus delta 1 minus delta 2 times the other factors, modulus squared.
In this, that one bar and that one bar are these the same?
No, they are independent. Delta 1 and modulus squared by definition means you take the bar of the deltas.
It's not modular square. It's your.
So it's not modular square. It's a new modular.
Yeah, that's why I wrote it explicitly to warn you that I was introducing the treacherous notation.
F should be barred as well here. You want the left-hand side to be real.
No, I don't.
Okay, so if F is IZ,
Well, as soon as
the modulus square of IZ would be.
Yeah. F is not barred at all. It's the same function. So that's really a tricky notation. Yeah, sorry, but it's very convenient. As in here.
In practice, all of your f's are going to be kind of some Taylor expansions.
Yeah,
In,
probably.
in delta and z with real coefficients. So
Yeah, I guess in practice it doesn't really.
I don't want to assume what the f's are going to be. But
No, in practice, F could be, I mean, I will use that for conformal blocks, for example. They also depend on the central charge, but the central charge could be complex, and I don't want to conjugate it. So it's really F. Yeah.
In the holomorphic case, you also introduce C and B, but no, some coefficients.
No, so in the holomorphic case, I didn't write the coefficients here for the correlation functions because I wanted to wait until I knew the dependence on z bar, basically. Because essentially, my formulas which I had over over some which I just erased. I mean, this was proportional, but proportionality meant I could have functions of Z bar, which means, if you want, anti-holomorphic functions of Z. But now I have fixed the anti-holomorphic dependence as well, so I can write them as real constants.
Sorry. If you put in inside your absolute value squared, if you put in I,
it stays I.
You get -1 out.
No, you get I again.
Times I.
Yeah, right.
And then you get -1.
Yeah, -1, yeah.
Yeah.
Thank you. Okay, so now the motivation also to introduce my right moving sector was to have single valued correlation functions. So are these correlation functions single valued? Well, you can study it now from their explicit expressions. For example, the 2-point function, you can do some monodromy where Z12 goes to E2 pi I Z12. So that's what happens if Z1 goes around Z2, one circle. And this should stay the same. And for this to be true, you'll have a constraint on the conformal dimensions. The constraint is that delta 1 minus delta 1 bar has to be a half integer. So that's the spin. Conformal spin S1 has to be half integer. And similarly, if you look at the 3-point function, if you do the same operations, you get a constraint on the conformal spins, which is that S1 plus S2 plus S3 has to be integer. Okay, so then I will consider another axiom which we had, which was permutation invariance. So in the correlation functions, it should not matter in which order I write the fields. Everything should stay the same if I permute them. But these formulas are not manifestly invariant under permutations, in fact. And permutation invariance gives you a constraint now on the structure constants. So the constraints are B21 equals -1 to the 2s1, B12, and C. So now sigma is some permutation, sigma of 1, sigma of 2, sigma of 3 is -1 to the, sorry, not -1, the sign of the permutation sigma to the S1 plus S2 plus S3, C1, 2, 3. So, and now what happens if I have a 2-point function of a field with itself? And I mean the same field, not a field with the same dimension, but really the same field. So if it's the same field, I must have B21 equals B12 in this case. And therefore, minus to the 2S1 is 1. So S1, the spin has to be integer. So in other words, if all fields commute, then their spins are integer. And in fact, most of the fields we would consider as integer spins. But I could still consider half integer spins, but then I would have to relax my commutativity and have fields which anti-commute. So fermions, if you want. And in fact, you could relax it further and have parafermions. That is a more complicated rules, monodromy rules.
Can you show that B12 is non-zero?
Sorry?
Another solution would be that this constant is 0, right?
Right. But typically, if you have a field with a 0 2-point function, I mean, its correlation functions will tend to vanish. So it will decouple. Okay, so that concludes the study of the, well, correlation functions and their single valuedness. And now I'm reaching, well, I hope you're not too tired because I'm reaching a really important conceptual point, which is how we will solve this solvable CFTs, which is by using crossing symmetry. So I want to introduce crossing symmetry equations, which will constrain the structure constants now. And to write these crossing symmetry equations, I need to introduce conformal blocks. So to do that, let me start again with operator product expansion. I mean, everything follows from the existence of operator product expansion. So let me summarize again what we learned about operator product expansion, especially that now that we know about having two Virasoro algebras. So V1, Z1, V2, Z2 is a sum. Now let me write this sum over a basis of primary fields. So I sum over all possible primary fields. I have a structure constant Ck12, and then I have some things which are fixed by conformal symmetry. So Z12 to the delta k minus delta 1 minus delta 2, sum over descendants, Z12 to the L, F, the OP coefficient. So F delta L, delta K, delta 1, delta 2, all this modulus squared, because I have a sum of left moving descendants, but I also have a sum of right moving descendants. They come with the similar coefficients F and similar dependence on Z. Now all this is applied to these descendants, LL bar, VK, of V2. So now that's the form of the OPE. And the idea is to insert this OPE inside correlation functions and see what constraints we obtain. So we'll begin with the simple case of 3-point function. But we want to make our life notations a bit easier by omitting all this stuff whenever we can afford it. So whenever we can, we write this OPE as P1 V2 equals sum of K CK12 VK.
But you also get C12 bar.
Yeah, C12 bar. Well,
I mean the C12 bar. I mean the coefficient.
No, this coefficient now is the same. I mean, here you have only one coefficient times something which is both depend on Z and Z bar. And here it's the same. For the OP, you have one coefficient times this thing. Okay, so the simplified notation for this OP is just that. The product of two primary fields is a linear combination of primary fields with some coefficients C. And basically, conformal symmetry takes care of all the rest. It takes care of the dependence on Z, and it takes care of the sum of the descendants. So here I'm writing only what's not fixed by conformal symmetry. So what happens if I start with a 3-point function, V1, V2, V3, and apply this? Well, I do the OP V1 with V2, and I get some VK12, VK V3. Okay, and this is essentially a 2-point structure constant now. But to simplify things, I will assume that Bij is of the type delta Ij. Yeah. So I assume that the fields Ij not only have the same conformal dimensions, which they need to have the same dimensions if the 2-point function is not 0, but I assume really that they are the same fields, otherwise it's 0. If you want, I can diagonalize the 2-point functions. So if I do that, I'm just obtain sum of a k, k12, and then this 2-point function becomes delta k3, 3. And so due to this delta, I can perform the sum, and I get C3, 1, 2, V3. So in my simplified notations, my 3-point function is C1, 2, 3. So we get this rather trivial but important result that the OP coefficients here, C1, 2, 3, is determined by the 3 and 2-point structure constant.
When you think Bi equals to 1 by renormalization.
So yes, so in many cases you could be the 2-point structure constant to 1 by a change of normalization of the field. So you can do some some normalization of this type. Vi of z goes to some lambda I vi of z, and if you do it, you can eliminate b. So I'm keeping b actually to make things simpler. Because if you are doing this type of thing, well, basically the coefficient you need is essentially square root of b. But then, indeed, if you do that, you get square roots in all your formulas later. So it's better to have another normalization of things where b is non-trivial, but where you don't have square roots. Okay, so that was just using an OP inside a 3-point function, but now the interesting thing is to do it in a 4-point function. So we start with a 4-point function, v1, v1, v4, v4, and we insert this whole OP here of v1 with v2. So essentially we get a sum of some ck12, and then a lot of stuff, and eventually we get to a correlation function of L bar vk of v2, v3, v4. Right? So we have reduced a 4-point function to a 3-point function. So now this 3-point function, well, the claim is that essentially we know it, because it's a 3-point function of arbitrary descendants, but descendants are determined by primaries. So this 3-point function should be proportional to the structure constant times some function g modulus squared. So g, if you want, g L delta k delta 3 delta 4. And this function is completely determined by conformal symmetry. So in principle, we know it. So eventually, I'll end up with a sum of ck12, ck34, times some object which comes as a modulus squared. Let me call it fs delta k. And this fs delta k is what we will call a Virasoro block. And to be explicit, let me write this S-channel Virasoro block. So this block is just the following. Okay, so to write it, to make life simpler, I'm assuming again that V1, V4 are Z0, infinity, and 1. So then it's just a function of Z. And this function is Z to the delta minus delta 1 minus delta 2 times the sum of the descendants of Z to the N F delta L, delta 1, delta 2, G, L, delta, delta 3, delta 4. So now by this choice of coordinates, this function is just now a number. This G is just a number because D2, D3, D4 are just fixed. So this is really a series in powers of Z with some coefficients here which are known numbers. So in principle, with what we've seen in these courses, you can compute this conformal block order by order in Z. I mean, you probably should not do it. Maybe you should do it up to order 2 in order to get an idea of how this works, but please stop at order 2. Otherwise, I'm not sure you'll be even here for the next course. Yeah, that's not really how we compute these conformal blocks. I mean, these are universal quantities, the very basic, the basic special function of 2D conformal field theory, if you want. So they are computed by much more efficient methods. Okay, in principle, they are defined like that, and they could be computed like that.
They depend on data.
Sorry?
They're just functions of data.
Well, they depend on deltas on the conformal dimension. They also depend on the central charge, right? I mean, this F, they depend on the central charge. So to be maybe explicit, this is so this Virasoro block. Well, it depends on the central charge. It depends on delta 1, delta 4. It depends on Z. Now, what appears is the modulus square of this block. So that's really what I want to call a conformal block, as opposed to a Virasoro block. So G delta of Z, which is defined as F Z squared, is a conformal block. Okay. So then the nice thing is that I could do other OPs in the same 4-point functions. I have done V1 with V2, but let's do V1 with V4, for example. So I will collect the results of that in a table. So I started with the S channel. So in the S channel, we've done the OP V1, V2. We've obtained structure constants here, 4-point structure constants. So if I look for D, S, K, which are just CK12, CK34. And we have a block, a Virasoro block, which when Z goes to 0, behaves as Z to the delta minus delta 1 minus delta 2. And we have a graphical notation like that for this decomposition into conformal blocks. But I could do it in the T channel. I would do V1, V4. I would get the T channel, the 4-point structure constant, which is what? Can anyone guess it? Yeah, C14K, CK23. Then I get a T channel block, which now becomes singular at Z goes to 1. Well, it's also singular at Z equals 0, but we define it as a series around Z, a series expansion around Z equals 1. Well, it's not quite a series. It starts with a power, which is just the delta minus delta 1 minus delta 4. And that corresponds to this diagram. And then, oh, sorry, that was K. And that's not finished. I have a U channel where I do the OP V1, V3. I have a U channel structure constant, which is CK13, CK24. I have a U channel block. When Z goes to infinity, this one is a bit tricky because fields at infinity, you have to be careful how you define them. But we've seen how to do it. So if you do it carefully, you should find delta plus delta 1 minus delta 3 here. And it corresponds to essentially to this thing. So 1 and 3 are related, and 2 and 4 are related with K here. So we have these 3 different decompositions of the same 4-point function, and therefore they have to agree. So the agreement of these decompositions is, well, very schematically written as, well, each decomposition is a combination of conformal blocks here. With some coefficients called 4-point structure constants. So that's the same for all 3 channels. And this equality is called crossing symmetry. Well, a small subtlety is that I'm writing the structure constants with indices k, but I'm writing blocks with indices delta k. I want to emphasize that blocks are really determined by conformal symmetry, so they can only depend on the conformal dimensions. On the other hand, this could depend, well, you could have several fields with the same dimension, so in principle, I must have a dependence on the index of the field k.
When it depends on Z.
The dependence on Z, yeah, it's in the blocks. Sorry. So each one of these blocks depends on Z, whereas the coefficients here are constant. Okay, so these equations are, well, what is known and what are the unknowns in these equations? Well, the knowns are the blocks. Well, they are known in principle. It may be complicated in practice, but you should know them. What is unknown is the spectrum over which you sum, so the set of primary fields which appear, and the structure constants D. So if you want, this is a set of linear equations for the structure constants, but it also constrains the spectrum. On the other hand, if you remember that D is supposed to be a combination of 2 and 3 point structure constants, you could view it as a nonlinear equation for the spectrum and then the 2 and 3 point structure constant. Well, these objects, if you want, they are called CFT data. And they are called CFT data because if you know them, in principle, you can compute any correlation function. Because if you start with the n-point function, you can do operator product expansions and reduce it until it's, if you want, a 2-point function. And you'll get just a combination of this data. And conformal blocks, of course, which you are supposed to know. So these CFT data are constrained by crossing symmetry. And well, a legitimate question is whether there are more constraints. I mean, what if I take a 17-point function and decompose it in all possible ways? I mean, would I get extra constraints on the structure constants? And who thinks the answer is yes? And who thinks the answer is no? Oh, so a few people are still thinking something. So. But most of them are not, apparently. So. Yeah, the answer is indeed no. I mean, I don't get more constraints by studying higher correlation functions. And the reason is that basically this crossing symmetry is equivalent to associativity of the OPE. I mean, these equations are derived from the fact that in the same 4-point function, I can do various OPEs in various order. But in fact, it's an equivalence. If you solve these equations, the OP is in fact associative, and once it's associative, I mean, no matter how many OPs you do, I mean, you don't have more constraints. Okay. Yes.
In this crossing symmetry equations, you mentioned that the conformal blocks are known. They're known each as a series expansion around a particular point, right? Like different points. Is that enough still to sort of nail what are the D's and to solve?
Yeah, that's a very good question, because here you have a series expansion, and you might wonder if it converges, and if yes, for which values of Z. Because if you want to compare these decompositions, well, you have to find points Z where both decompositions exist. And indeed, the radius of convergence of this expansion, well, it's not necessarily infinite. And in fact, if you compute it like that, typically the radius of expansion for S-channel block like that will be 1. So if you have your point Z, Z now, so we have 0, 1, and infinity, and your Z, you can put it in this circle, and you will have a convergent expansion for the S-channel block. Well, what I'm saying here is basically a conjecture. I mean, I don't think it has been proved. Okay, it's believed to converge until this point, because at this point you reach another field, so you have a singularity due to the presence of a field at 1. Well, that's already good enough to do some crossing symmetry, right? Because if the OP at 1 has also radius 1, then you have an overlap in this region where you can indeed use this crossing symmetry equation. Okay, however, in practice, that's not what we do. I mean, in practice, we reformulate the conformal blocks as a series in another variable, which converges over the whole complex plane. So yeah, so depending on how you compute the block, you get a different radius of convergence, so it can make a big difference technically.
the analyticity behavior is cut starting from 0, 1.
Yeah, so this Virasoro block, indeed, it has non-trivial analyticity properties. So it's not single valued. So indeed, it has, well, I think you can basically say it has a cut from 1 to infinity. Yeah, you can analytically continue from 0, but at some point, things happen. I mean, you have a very non-trivial essential singularities at 1 and infinity. Okay, other questions on recrossing symmetry? Okay. So I propose to continue for maybe 10 minutes in order to start the section 2, which is about sketching some simple solvable conformal theory. Because so far, I mean, we've done the general formalism, which applies to basically any two-dimensional CFT, but now we want to focus on the ones that are solvable. So, in fact, the CFTs I will try to solve, or at least introduce, I mean, they haven't been solved by this conformal bootstrap method. Well, not all of them. Typically, they've been approached by, well, different methods. So, if you talk about minimal models, well, essentially, they were derived using a modular bootstrap. So, looking at the torus partition function. Historically, Liouville theory, where it was defined using fast integrals. If you look at loop models, by which I mean the ON or Fox models, they were constructed using statistical sums on the lattice. Or if you, I mean, that was for Liouville theory with a generic central charge, but if you look at Liouville with t less than 1, well, originally, well, there was some analytic bootstrap involved, but there was also numerical bootstrap. So, but we don't want to have to learn different methods to deal with different CFTs. I mean, I will not at all follow the historical approach. I will try to fit all of them in a simple approach based on, well, on the fusion rules of degenerate fields, which we've seen today. And well, this is not only for simplicity, but this is because I think this approach, I mean, you could generalize it to other CFTs, at least other 2D CFTs with well, with other symmetry algebras, like W algebras or Western-Newton methods.
But the chiral rules are defined for W algebras also. I thought you said there are some subtleties in solving the W algebras.
Yeah. So I think the main problem with W algebras is that dissonants are not determined by primaries. So you have fusion multiplicities, which are non-trivial. But it doesn't prevent you from applying the method. I mean, you won't go that far. I mean, you'll hit technical roadblocks. In particular, the generalization of Liouville theory called conformal Toda theory has not been solved yet. But I mean, I think if you try to solve the W minimal models, then probably you could do that by this approach.
Yeah, I mean,
yes.
Sorry, so solve, you mean, say, solve for the CFT data?
Yes.
There. And so then principally you construct correlation functions of primaries.
Right. So solving means essentially determining the CFT data, and therefore you are able to, in principle, compute all correlation functions on the sphere, well, provided you can compute conformal blocks.
I have the feeling if you were studying a conformal field theory on the upper half plane, life would be much easier. From what you said, I would have to care about Z bar and everything.
Yeah, so on the upper half plane, you would think life is easier, or maybe I just, so some people think you should start with boundary CFT, which lives not on a two-dimensional space, but in one dimension. And yeah, there are some algebraic approaches which start with the boundary CFT. However, to have Z and Z bar is nice because you can do monodromy in the plane, and you have non-trivial constraints from single values, which you don't have on the line. Well, you still have them on the upper half plane. So upper half plane is not making your life so simple, because now the 1-point function is no longer 0. Well, on the plane, the 1-point function had to vanish unless delta is 0, but that's no longer true on the upper half plane. So yeah, I think the sphere is nice. Well, I try to show it. You can go quite far on the sphere. Okay, so I want to introduce, to discuss the notion of a spectrum, because I've been a bit vague about it. Now I want to make it more precise, because it's a rather subtle notion, especially in non-rational CFTs. So, well, I've been talking about rational and non-rational CFTs, so let me define it. So a rational CFT is the CFT such that the number of primary fields is finite. So now, if I consider an OPE, I've been writing an operator product expression as a sum over k. So this k, so let's say it belongs to some S12. And so this S12 is what I would call an OPE spectrum. So the set of primary fields that can appear in this OP, well, that do appear in this OP. And we've already had some strong constraints on this object. Like when one of the fields was degenerate, then the OP spectrum was just a set of two. On the other hand, if I consider a 4-point function, again, I want to decompose it into conformal blocks. Let's say S-channel conformal blocks. And then this k in the decomposition belongs to, well, a spectrum S, which I would call S upper index S, like for a S-channel spectrum. And this S-channel spectrum, S is just the intersection of two OP spectrums, S12 inter S34. And next, if I consider the whole CFT, well, it has a spectrum S, which is basically the union of all these spectrums. So the spectrum, which I would call physical, it has to be such that if I and j belongs to S, then, well, all Sij is included in S. So all fields I get in the OPEs should also be in the physical spectrum. And then I want to define an S tilde like an extended spectrum. Extended spectrum is just if you can consistently add some fields to your spectrum. So these fields, you don't need them, but maybe you can add them without breaking anything, without breaking crossing symmetry in particular. So that would be just a larger spectrum which obeys the same constraint. Ij belongs to S tilde implies Sij includes in S tilde. So this property, if you want, is called the closure under OP. So why am I doing this like hair splitting and distinguish extended from physical spectrum? It's because it's really needed if you want, for example, to solve Liouville theory. And in fact, we've already used that without saying it. Because I've been using the energy momentum tensor T of y in order to derive some constraints on correlation functions or OPEs. But nobody tells me that T of y really belongs to the CFT. Or the question is whether when you do some OPE, you will ever encounter the energy momentum tensor. Like maybe you do, maybe not. And in fact, in Liouville theory, you never encounter T in any OPE. So your theory is consistent without the energy momentum tensor. And yet, I mean, technically, it's very useful to introduce the energy momentum tensor. And all correlation functions that involve it are consistent. And they obey, well, they obey everything, associativity, crossing symmetry, etc. So that's the motivation for having an extended spectrum. And we'll see examples of that, including, well, we make a great use of degenerate fields of the type V2, and in particular, to derive the non-trivial constraints on correlation functions, but we can use it even if it doesn't belong to the spectrum. And that will happen in Liouville theory as well, but also in the ON model. So if you want, there are two notions. So a field is physical if it belongs to the physical spectrum, and a field exists if it belongs to some extended spectrum.
And you can also define a general notion of restricted spectrum.
Yeah, so indeed, we could have a restricted spectrum, which is your spectrum where you remove fields such that the CFT remains consistent on the sphere. Because if you do all these kinds of operations on the torus, typically it breaks down. I mean, you lose modular invariance. But on the sphere, you just have to obey this closure on the OPE. So in minimal models, for example, you can find subsets of fields, typically, which are closed on the OPEs, and then you can indeed define a restricted spectrum.
What makes a spectrum physical? It looks like you have this notion of a spectrum, which is something that's closed under the OPE. But among these possible spectra, one of them is the physical one.
Yeah, so I think it's subjective, what you call physical. If you're really interested in the torus, you want modular invariance, and that will typically single out a physical spectrum. Yeah, physical spectrum, or you could say it's the observables you are really interested in. So I don't know. I mean, I just made this up. I mean, this is not really standard in the literature, but I think it's useful to understand what's coming next. I don't have a clean definition of a physical spectrum, really.
But it should be independent of any Riemann circle. You could guess that a good conformal field theory could be put on any surface.
Yeah, that's one way to constrain or even single out the physical spectrum. You're requiring consistency on higher genus.
I guess you can define it to be this space of states on S1.
Yeah, but how do you define it a priori? I mean, we are in the bootstrap approach, so we only have consistency conditions. We don't have ab initio determination of the space of states. So yeah, if you start with a Lagrangian or some other definition of your CFT, maybe you get a specific spectrum, which then is the physical spectrum. Yes?
I don't really know if it's related, but for instance, in the Ising model, there is the famous rational theory with only 3 primary fields, but it doesn't allow you to compute correlations of certain defects in the Ising model. You have to introduce other fields, compute those, and you get a consistent conformal field theory with those.
Right, so that's an excellent example, in fact. So in the Ising model, if you start with the minimal model, you just have these 3 fields, and there's not much you can do with that. And if you want to compute like defects, or if you want to compute connectivities of clusters, then you need an extended spectrum. But yeah, in this case, I would even call the minimal model a restricted spectrum, because it's not very interesting. And, yeah.
What about in the 3D Ising model? Did people look at extensions of the usual spectrum of the 3D Ising?
I don't know. I mean, I think what people are studying in 3D, as far as I understand, is the counterpart of the minimal model, but it's already difficult enough, right? but if you wanted to study non-local objects, like these cluster connectivities, which you can also define in 3D, and probably you will need to introduce extra fields in your spectrum.
But then you lose some of the axioms. Locality is what?
Unitarity, for example.
No, wait, so yeah, you lose unitarity, yes, but you don't lose locality. I mean, that's the nice thing, and it's not obvious at all, but these connectivities, which are very non-local objects, which are probabilities that 2 points belong to the same cluster, well, they are described by correlation functions of primary fields, of the primary fields which we have defined and which are, in a sense, local objects because they have a nice OPE when they come close together, but on the other hand, they don't influence each other if they are too far.
And when do you lose unitarity?
So, I'm not sure exactly why. I mean, do we have a general argument why studying these non-local objects leads to loss of unitarity? So unitarity is the property that essentially your space of states has a positive definite scalar product, and also the structure constants are, well, positive, well, some of them. And yeah, it's a fact that it's related to this to this locality of objects you're considering, but why exactly? So maybe.
For Ising, for instance, the central charge is what it is, so you know there are only finitely many representations which are unitary, and some of these non-local fields, they just don't belong to the set.
Right. So in this case, since unitarity is so restrictive, you would just see that you can't compute these objects by using what unitarity allows. But yeah, that's a statement. That's not really an explanation. Yeah.
The unitarity has to do with Z and Z bar becoming real. So,
not really. So unitarity has to do with having in your Verma module, for example, you want to have a scalar product which is positive and which also is compatible with Virasoro symmetry. So you want basically L0 to be self-adjoint because you want to interpret it as your Hamiltonian. And this implies all sorts of things. So this implies, first of all, Ln driver equals L minus N. This implies that the central charge is real. And then if you look at the Verma module, it implies that delta is positive.
But I thought this conformality theory they can define with real time sometime, or Hamiltonian with a real time action. And I would think unitarity would be more related to this kind of. No, there was this whole thing, reflection, symmetry, reflection, positivity.
Right. So that's one way to formulate unitarity in an approach in terms of correlation functions. Yeah. But maybe we can discuss unitarity after the lecture. But I think, it's really not part of the subject, and yeah, probably we should stop here.